You know, every single time you send an email, watch a video, or even just wiggle your mouse across the screen, you're tapping into a system that's built on a language of, well, incredible simplicity. It's a language that uses just 2 digits to create our entire digital reality. Today, we're going to pull back that curtain and actually learn to speak it.
All right, let's get into it. Here's our game plan for this little journey under the hood. First, we'll cover the absolute basics of how computers talk. Then, we'll actually learn how to translate their language. After that, we'll see the clever shorthand that coders use, find out where you're already seeing it every day, understand how computers do math, and wrap up with a really neat trick they use for negative numbers.
You have to remember, at their very core, computers are just a mind-boggling collection of tiny switches. We're talking billions of them, and each one can only be in one of 2 states, on or off. That's it. So the huge challenge for the pioneers of computing was, how do we represent everything, all of human knowledge, with just those 2 states? And that really brings us to the biggest question of all, doesn't it? How is it even possible? How can every photo you've ever taken, every song you've streamed, every complex world in a video game be built from something as simple as a 1 or a 0?
Well, the whole answer is in the number system. We humans are used to what's called the binary system, or base 10. Why base 10? Simple. We have 10 fingers. It uses 10 digits, 0 through 9. Computers, on the other hand, with their on and off switches, they use the binary system. That's base 2. The 0 simply means off, and the 1 means on.
Okay, so now we know the alphabet. Just 2 letters, 1 and 0. So let's figure out how to actually read the words. And honestly, it's way simpler than you probably think.
Just take a look at this. In our normal number system, each column represents a power of 10, right? The ones place, the tens place, the hundreds, and so on. Well, in binary, each column is a power of 2, so you have the ones place, the twos place, the fours, the eights, 16, and it just keeps doubling. To figure out what a binary number, like 11101110, actually means, you just add up the value of every single column that has a 1 in it. So that's 128 plus 64 plus 32, we skip 16 since there's a 0, plus 8 plus 4 plus 2, and that gives you 238. It's really as simple as that.
Okay, so reading binary. Pretty straightforward. But what about writing it? How do we take a number that we understand, like say 142, and translate it into the ones and zeros a computer can actually process? Well, there are 2 really great ways to do it. The first one is kind of the intuitive way. You take your number, we'll stick with 142, and you just find the biggest power of 2 that can fit inside it. In this case, that's 128. So you put a 1 in the 128's column. Then you see what you have left over, which is 14, and you just do it all over again until you hit 0. Now, the second method is much more systematic. It's pretty much foolproof. You just take your number and repeatedly divide it by 2. You write down the remainder each time, which of course is always going to be either a 1 or a 0. And when you're done, you just read those remainders from the bottom to the top. The cool thing is both methods will give you the exact same answer every time.
All right, so we've cracked binary, but there's a practical problem. For a computer, a massive long string of 1s and 0s is no big deal. But for a human programmer who's trying to find one tiny mistake in that string, it is an absolute nightmare. We needed a better way.
And I mean really long. A single photo from your phone can be represented by millions, maybe even billions of these 1s and 0s. Trying to read that directly is it's impossible. And this is where hexadecimal, or hex for short, comes to the rescue. It's a base 16 system. Now, to get 16 unique digits, it uses our normal 0 through 9, and then it just borrows the letters A through F for the values 10 through 15. And the reason this is so absolutely brilliant is because 16 is a power of 2. It's 2 to the power of 4, and that creates this perfect, clean bridge between binary and hex.
And what's so interesting about this slide is it shows that magic connection. You should think of this table as the Rosetta Stone for programmers. It perfectly translates every single possible combination of 4 binary digits from 0000 all the way to 1111 into one single easy-to-read hexadecimal character. This little table is the key to the whole thing.
And because of that, converting a massive binary number into a much shorter hex number is incredibly easy. You literally just start from the right-hand side, break that big binary string into little chunks of 4, and then you just swap out each chunk for its hex symbol from that table we just saw. That is it. And this shows you just how powerful that is. I mean, look at that long binary number up top. It's just a jumble of digits, right? It's noise. But by breaking it up into those groups of 4 and just translating them, it becomes the clean, simple, and much more memorable 21FD.
So you might be thinking, okay, this is neat, but is this just for computer scientists and programmers? No way! You interact with hexadecimal codes every single day, and you probably don't even realize it. You'll find it defining all the colors you see on websites. It's used in those cryptic error messages you get when your computer crashes. It's in the unique MAC address of your phone. Think of that as the permanent hardware fingerprint that lets it connect to Wi-Fi. And it's a huge part of the new IPv6 internet system, which is what allows all our billions of devices to find each other online.
And here is that big aha moment. When you see a screen like this, you are looking directly at hexadecimal. That code, something like 0x4a, it's not random gibberish. It's a memory address, written in hex, telling a technician exactly where in the computer's memory bank the problem happened.
And here's another one you see all the time. Every single color on the web is defined by a 6-digit hex code. The first 2 digits control the amount of red, the next 2 control green, and the last 2 control blue. So a code like FF0000 means maximum red, 0 green, and 0 blue. It's a fantastically efficient way to represent over 16 million different colors. Okay, so we can read and write in the computer's language. But how do computers actually use it to perform calculations? And maybe more importantly, where can they get it wrong?
You know, binary addition works exactly like the addition you learned in elementary school. You add everything column by column, from right to left. The only rules you need to know are super simple. 0 plus 0 is 0. 1 plus 0 is 1, and 1 plus 1 is 0, carry the 1. That's all of it. A computer can do millions, even billions of these simple operations every single second.
But there is a catch. See, computers have a fixed amount of space to store a number. It might be 8 bits or 16 bits or 64. So what happens when the answer to a math problem is too big to fit into that designated space? Well, that's what's called an overflow error. It's like trying to pour a gallon of water into a pint glass. And this is a perfect example. We're adding 2 numbers in an 8-bit system. The math is correct, but the result needs a 9th bit. See that little 1 that was carried over to the left? Well, since the computer only has room for 8 bits, that 9th bit just falls off. It vanishes, and the computer's left with a completely wrong answer. Now, this might seem like a small technical thing, but this exact kind of error had catastrophic real-world consequences in 1996 when the Ariane 5 rocket exploded just 40 seconds after launch, all because a number got too big for the space it was supposed to fit in. So, we can add, and we know about the limits. But everything we've talked about so far has been positive numbers. So how does a system of just on and off switches represent something like, say, -67? There's no switch for a minus sign. This is where things get really, really clever. The solution is this really elegant system called 2's complement, and it's one tiny change that has huge implications. In an 8-bit number, the place value of the leftmost bit, the one that's normally positive 128, is just changed to negative 128. All the other place values stay exactly the same. They're all still positive. So the most important point is that this system gives us a dead simple 3-step recipe to find the negative version of any number. You start with the positive binary number. Then you flip all the bits, so every 1 becomes a 0 and every 0 becomes a 1. And for the last step, you just add 1. It honestly feels like magic, but it works perfectly every single time. And there you have it. From a simple on-off switch to a base 2-number system to a clever shorthand called hexadecimal, and finally a truly brilliant trick to handle negative numbers. This is the absolute bedrock of modern computing. It really makes you wonder, doesn't it? What other simple, elegant languages are running just beneath the surface of the technology we use every single day?